Hi, this is David Follis, and this is our continuation of our video series on why WebSphere Application Server on zOS. It's sometimes common to hear people speak of WAS on Z to mean both WAS zOS and WAS for Linux on System Z. In one sense, that's okay, given our earlier WAS is WAS statement regarding the common and consistent application interface layer. But in another sense, the generic WAS on Z phrase can lead to confusion about what function is available for WAS on Linux on System Z as compared to WAS on zOS. The two are not the same thing. They do share a common and consistent open standard application interface specification support. That's the WAS is WAS statement. But WAS on Linux for System Z does not have the attributes of zOS to work with. There's no WLM, SMF, SAF, RRS, or parallel sysplex. Those are all functions of the zOS operating system. WAS for Linux on System Z does derive benefits from running on the reliable System Z hardware. The IFL specialty engine makes the financial model attractive, and the ZVM hypervisor is an excellent virtualization platform. This chart offers a summary of how WAS for Linux on System Z may run on the System Z hardware. First, it runs on an IFL specialty engine, so the acquisition cost of the processor hardware for Linux is less. Second, it's capable of running either native in the LPAR, which isn't very common, or virtualized as guests on top of the ZVM hypervisor in an LPAR, which is much more common. One of the advantages of running multiple Linux guests on ZVM is that ZVM provides a good set of monitoring tools to keep track of the operations of the guests. And ZVM is really good at managing the virtualization of LPAR resources up to the many guests it supports. That's why System Z and ZVM is such a good virtualization platform. The hypervisor, ZVM, is very good. The hardware, System Z, is very good. And together it's capable of supporting hundreds to thousands of Linux guests. The distributions of Linux that are supported is shown on the chart above, along with a URL for the latest information on supported Linux distributions. Once the Linux operating system is in place, then WAS on that Linux operating system is no different than WAS on Linux running on IBM Power or Linux running on an x86 platform. WAS for Linux is WAS for Linux, and WAS for Linux is very much the same as WAS for AIX, which is very close to WAS for Windows. So what are the benefits of WAS on Linux for System Z? That's covered next. This chart summarizes the value statement of running WAS on Linux for System Z. The key value is the ability to consolidate, which saves considerably on environmental costs such as power and floor space. There's also the potential for saving on licensing charges for software that's priced on a per-core basis. But any considerations of licensing costs should first be properly analyzed rather than assumed based on this presentation. The disaster recovery process for Linux images on System Z is made easier because of the consolidated nature of the System Z platform. With proper planning and configuration of the storage resources, a System Z image running ZVM and Linux can be fairly easily started on a System Z platform at a disaster recovery site. Disaster recovery of a server farm with hundreds or thousands of separate physical servers makes DR much more challenging. The ZVM hypervisor also provides an excellent provisioning platform for rapid deployment of new instances of Linux and WAS on those Linux instances. IBM's cloud offerings around System Z are built on this capability. Finally, an LPAR in System Z running Linux is capable of accessing hypersockets to transfer TCP/IP networking between that LPAR and other LPARs, including an LPAR running zOS. We often see WAS on Linux for System Z using hypersockets to access data systems, DB2, KIX, IMS, running on zOS and another LPAR. But the value statement of WAS on Linux for System Z can't claim the kinds of things we covered for zOS, because those functions are simply not available to Linux for System Z. This chart is showing the performance improvements seen in WAS over time with changes in two variables: the version of WAS for Linux on System Z and the hardware platform on which the test was run. The trend is obviously upward. The end-to-end improvement is a factor of over 4 times better performance. As with any performance chart, this test was performed under controlled conditions with a specific sample workload with a specific system setup configuration. Performance results are a function of many factors, and your results may vary. The results shown on this chart are not a promise of performance gains and should not be taken as such. This chart should not be used for capacity planning. Other capacity planning tools for System Z are better suited for that role. This was a test of WAS on Linux for System Z throughput performance under the specified test conditions. The test conducted measured achievable throughput when the CPU utilization was pushed to near 100%. The aggregate performance is a normalized measure of achievable throughput, with the leftmost bar on the chart serving as the baseline value of 1.0. WAS on Linux for System Z started with a better performance profile in the WAS v6.1 timeframe than did WAS on zOS. Opportunities for WAS zOS performance improvements were greater and put in place, hence the 5.2x improvement on the earlier chart from start to end compared with WAS for Linux on System Z's 4.1x improvement. With WAS 8.5, the performance of each on the EC12 is roughly comparable based on this day trader test scenario. In this section, we'll take a somewhat brief tour of the topics of disaster recovery and high availability. Both are actually somewhat deep topics to cover in full detail, which in any event would be outside the scope of this presentation. The objective of this section is to demonstrate how WAS zOS has particular benefits for both DR and HA. The fundamental answer we'll end up giving is really what we've given up to this point, because of System Z, zOS, and Parallel Sysplex. Disaster recovery, or DR, the ability to relatively quickly restore service for a solution architecture at a completely different site, is a practice well known within the System Z and zOS world. The practices needed for successful DR for System Z runtimes is well known, and many companies have well-defined procedures in place that are invoked in the event of a site outage. The reason System Z solutions lend themselves to more effective DR processing is because by its nature System Z is a consolidated server environment. It's easier to execute a DR plan when all the components and artifacts of a solution architecture are accounted for and in place at the recovery site. It's far more difficult to execute a DR plan when the components and artifacts are distributed across a wider array of platforms, some of which are accounted for and some, sad but true, are not accounted for prior to executing DR recovery. Disk mirroring technologies make DR even more successful. When data updates can be mirrored to the DR site, then recovery can be accomplished using the mirrored data. Of course, that assumes all the data needed to run the total IT solution architecture gets mirrored. Here again, System Z has a legacy of tighter control on disk usage related to the solution architecture. It's not magic, it's simply based on a historical culture of consolidated management with careful accounting of what's needed for recovery. Given System Z and zOS lend themselves to effective DR execution, then WAS zOS follows on top of that. The artifacts that make up a WAS zOS runtime are standard zOS things: datasets, JCL procedures, SAF security profiles, WLM classification rules. All those things manifest down to disk storage used by the operating system, and given the system's disk storage is mirrored, then the DR recovery, including WAS zOS, will be successful. The same is true of WAS on Linux for System Z, since storage around ZVM can also be contained to an understood set of disk resources. Mirror those disk resources, and recovery of the ZVM environment and all the related Linux instances comes along with it, including any WAS for Linux on System Z configurations built in the Linux instances. WAS for zOS and WAS for Linux on System Z benefit from running on a platform environment for which successful disaster recovery planning and execution has been a long-standing practice. The runtime and application configurations for WAS on both those operating system platforms manifest down to disk storage that is, typically and historically, well managed, accounted for, and mirrored to the DR site. Given that basic premise, then DR of WAS simply follows along with DR of the operating system and all its associated components. That's not to say that DR can't be done for distributed architectures. It can. It's just that the management of the environment for distributed architectures has proven to be more challenging, and ensuring all the pieces are accounted for is not always accomplished. Unfortunately, as is too often the case, the missing pieces are not discovered until an actual DR recovery is called for. The topic of high availability is one that requires a good understanding of all the layers of an architecture, and a good understanding that 99.99999% availability is not necessarily easy and involves more than merely duplicated servers. The chart above shows a typical layered architecture from the lowest level of physical, buildings, up through the higher levels of logical integrity, transactions. There can be different interpretations of what the layers should be labeled. That's okay. The key is understanding that a solution architecture has layers of availability and recovery, and true HA involves it all. To illustrate this point, assume a case where a key application is down, but the server hardware on which it runs is available. In the truest sense of HA, is that environment available? No, it's not. The flip side of that is interesting to consider as well. Imagine that same environment where all key functions of that application are available, but one minor function is not available. Is the environment available? Well, maybe. That one minor function may not be critical to the business definition of highly available. That's why it's often useful to start the discussion of high availability by considering what things would constitute an outage. Those things you consider too valuable to be without would be things worth protecting. But other things may be acceptable within the context of what you're trying to protect. Protecting against every conceivable outage scenario becomes difficult and very expensive. It may be far more than the business requires. So be clear on what you're trying to protect against and design your topology based on that. Ultimately, what we're going to propose in this section is that System Z, zOS, and Parallel Sysplex offer a solid foundation for such a highly available design. We'll skip over site buildings in the layered diagram. We'll assume those buildings have sufficient integrity to run the server infrastructure. The issue of duplicated electrical circuits and duplicated network feeds from separate ISPs is a fairly well-known concept by facility staff. It's not directly related to System Z and zOS, but it's certainly true if there's only one electrical circuit and that one circuit is lost, then whatever that one circuit feeds is lost. Without a backup circuit, then all the layers higher in the stack become irrelevant since the whole environment has gone dark. The same holds true for networking to the outside world, which is why separate networking paths and separate network interface cards are typically employed. The server infrastructure layer is where System Z comes into play. Earlier we spoke of the inherent reliability of the System Z hardware. That reliability is by design. The best way to recover from an outage is not suffer through it in the first place. Hence the extremely robust redundant features throughout the System Z design. The Prism hypervisor provides the ability to carve out separate OS instances on the reliable hardware. As noted earlier, Parallel Sysplex provides a clustered zOS environment with a shared data model in the coupling facility. The CF itself is capable of being redundantly configured. A Parallel Sysplex may be between LPARs on a central execution complex, or CEC, that is, the physical System Z server box, or across multiple CECs, across both LPARs and separate CECs, and even between buildings separated by geographical distance. A house is only as strong as the foundation on which it's built. That's true of an application architecture as well. The foundation in this case is the duplicated design points of the server machine and the ability to cluster zOS using Parallel Sysplex. That's the essential foundation on which the HA design is built. The zOS operating system is built upon a design for resiliency and reliability. We saw this earlier on the chart where we quoted from a presentation written by a retired IBMer who'd been part of the early design and had worked with zOS all of his 40-year career. zOS has the ability to remain active for long stretches of time without requiring a restart. The clustering offered by Parallel Sysplex provides the ability to have multiple instances of zOS organized into a logical group so that the loss of one instance still leaves others operational. Parallel Sysplex is a technology that clusters zOS system instances into a logical group. The zOS system instances may be separate LPARs on the same machine, LPARs on separate machines, or both. With respect to availability, one of the key elements of Parallel Sysplex is its support of shared data structures in the coupling facility and Sysplex-enabled data middleware components that take advantage of that. Parallel Sysplex provides a redundant data tier along with a redundant application tier. A system design that has the application tier duplicated but with a single instance of the data tier leaves the entire design vulnerable to an outage of the single data instance. Parallel Sysplex addresses that by enabling multiple instances of the data tier middleware with a shared data model in the middle. Each instance of the data tier middleware has access to the same data as any other instance. The signaling mechanisms of Parallel Sysplex provide the necessary communication to manage the data locks between the members of the data sharing group. The WAS version 8 alternate JNDI failover function provides a means of using cross-memory communication from WAS zOS to the local data instance, and, in the event that local instance is lost, then failover across the network to a surviving member of the data sharing group. In a high availability design, the application tier is made redundant as well. This is done with WAS clusters where application servers are configured in a cluster across LPARs in a Parallel Sysplex. The WAS zOS controller region is what listens for inbound requests, and in this design, each LPAR in the cluster would host a controller. That raises the issue of inbound request distribution, which we'll cover next. The issue of maintaining state data across the cluster must also be taken into account. That too will be covered in an upcoming slide. The WAS zOS servant region design provides an additional layer of redundancy behind the controller. At a minimum, a failed servant will be automatically restarted by WLM. If you configure multiple servant regions behind each controller, then it forms an inner cluster. Application hosting servants are duplicated with the applications resident in each. Two clusters then exist. The outer cluster, duplicated application servers with redundant controllers, in the inner cluster, duplicated application JVMs with redundant servant regions. When application servers are clustered across LPARs, it implies multiple controller regions, each with a set of listener ports on the TCP stack of that LPAR. Therefore, something must sit out front of that and route inbound requests to one application server or the other. This is not unique to WAS zOS. This is the case for WAS clusters on any platform. There are many front-end routing mechanisms available in the market today. They work with WAS zOS as well. A WAS zOS cluster is really no different from a distributed WAS cluster from a request distribution point of view. For example, all HTTP requests are going to flow across the network, and a WAS zOS cluster is simply a set of HTTP ports on the network, just like a distributed WAS cluster would be a set of HTTP ports on the network. The WAS zOS pause listeners command enhances the operations of request distribution. That command turns off the listener ports on the application server controller, which immediately makes that server ineligible from the point of view of front-end distribution devices. Work in those servers continue, it's just the listener ports go dark. That provides an important tool and a highly available design because it allows you to drain work away from a server for the purposes of planned outages. Sysplex Distributor on zOS provides a means of defining a virtual IP address that clients in the world can be configured to point at. That virtual IP address can be configured to automatically move to a surviving LPAR in the Sysplex in the event the original hosting LPAR is lost. The virtual IP is always present. Clients in the world never have to reconfigure. The DNS systems do not need to be updated for this to work. A fundamental principle in HA is the idea that clients will call back if a connection is broken. That means the routing functions in place must be ready to accept the callback and understand what remaining routing alternatives are available. There are many solutions in this space, and not all are based on zOS, but in the zOS space, the virtual IP support and Sysplex Distributor can be a worthwhile tool to deploy. Applications often maintain state information about the connected client and where they are in the particular process being worked. A common form of state information is the HTTP session object, which, when created, is maintained in the JVM memory heap of the server in which it was created. Stateful EJBs would also fall into this category, though they're somewhat less common than simple HTTP session state. The creation of state implies the need to route a subsequent client request back to the JVM in which that client state information is being maintained. That's what the phrase session affinity means. For routing to one of the controllers in the cluster, that's the responsibility of the front-end routing device. For routing from controller to servant, that's the role of the controller. What happens if the JVM in which a client session object resides is lost? If that session object has not been replicated, copied to other JVMs, or persisted, stored in a database, then the client would need to log back in and recreate whatever state information they had before. That's a potential hit to availability, so typically session objects are either replicated or persisted or both. WAS zOS supports both replication and persistence, just as WAS on the other platforms do. Session replication implies copying the session objects across the network to the other JVM. When the server cluster is across two LPARs on a System Z machine, the use of hypersockets allows network transport across the memory backplane of the machine. Session persistence may be done to DB2, which, in a parallel Sysplex with DB2 configured in a data sharing group, may be done by using JDBC Type 2 local persistence to the local DB2 instance, which is then immediately available to DB2 instances in the data sharing group on other LPARs in the Sysplex. When a WAS zOS application server has multiple servant regions, the same concepts apply, either replication or persistence. If replication, then the object does not need to be copied across a network, because WAS zOS will store session objects in a zOS memory data space held by the controller. The objects are copied to the data space and available to the other servants in the server. That's all cross-memory copying with no network involved. The final layer we'll discuss in this review is that of transaction recovery. When a high-volume system is processing transactions and there's an outage at some point, there's a good chance some of the transactions will be left in an in-doubt state. In-doubt transactions are those where the transaction manager is not certain of the state of the data commitment by each of the participants. That's a potential problem because data locks may be held for those transactions. Other transactions can take place, but any data held by those locks will be held until the transaction is resolved. As we mentioned earlier, RRS is the zOS component that serves as the transaction sync point coordinator between transaction managers and resource managers. RRS is Sysplex aware, and the transaction logs are maintained in shared data structures in the coupling facility. RRS instances run on each member of the parallel sysplex, and each has access to the transaction logs and shared data. zOS is RRS enabled, as is DB2, CIX, IMS, and MQ. If one of those transaction participants is lost, they may either be restarted on the same LPAR to recover the transactions, or restarted on another LPAR in the sysplex. So if a whole LPAR is lost, the transactions can still be recovered by starting the failed transaction participant instances on a surviving LPAR. They come up, coordinate with RRS to resolve the in-doubts, and then they stop. For zOS, a failed instance of a server cluster member that leaves some transactions in doubt can be handled automatically with the WAS High Availability Manager feature. HA Manager is available for WAS on all supported platforms. It detects the loss of a cluster member, and a surviving cluster member will work to resolve any transactions left in doubt. With zOS, Parallel Sysplex, and RRS, there's no need to make XA partner log file systems available across the WAS cluster. That's because RRS resides on each LPAR of the parallel sysplex, and the transaction logs are held in the shared data structures of the coupling facility. There are no XA partner logs and no worry about shared file systems. It's all part of the parallel sysplex design. And RRS processing to recover transactions is very reliable and very fast. Transaction recovery using XA partner logs is possible, it's just that the process is much faster and better on parallel sysplex. That's the overall message. HA involves a systematic review of the entire application and system architecture. The objective is to look for potential points of failure and to protect against them. Protection against outage is typically done by designing in redundancy and inspecting the system elements to make sure the redundant components are utilized properly in the event of a failure. High availability is not the exclusive domain of System Z. It's possible to configure relatively good high availability on non-System Z systems. The message here was that System Z, zOS, Parallel Sysplex, and WAS on zOS combine for a strong HA story. It's not that any one piece of that is the magic bullet that provides HA. It's that the entirety of the system working together provides the foundation for high availability and the higher level artifacts as well. When considering the cost of a given solution, the first level of cost is the cost to acquire the pieces that make up the solution. This is typically a relatively short-range cost view. Typically, though not always, this includes only the cost of the server hardware and software and does not include other factors such as space charges and energy costs. A broader cost perspective is cost of ownership, which typically takes a longer view, greater than 1 year and often in the range of 3 or more. It incorporates costs beyond the acquisitions of the hardware and software. The value statements of System Z solutions are commonly built around factors of consolidation, space, energy, staffing, and ongoing support. When compared to cost structures for distributed server farms, System Z solutions become favorable. This is particularly true the longer the time horizon that's considered. As is shown on the chart highlighted in yellow, a review of what kind of overhead burden is applied to existing mainframe environments is often enlightening. We've seen cases where most or all of the overhead costs of maintaining a data center are applied to the mainframe, even though other compute platforms are present as well. The mainframe environment typically pre-existed the others, and the cost accounting process was developed very early on when only the mainframe was present. Those cost accounting processes never changed as newer compute platforms came along. We've seen cases where the cost of the distributed compute platforms are applied as overhead to the mainframe. In that kind of environment, any cost of per compute cycle analysis naturally shows the mainframe is more expensive than others because the mainframe is carrying an undue burden of overhead fixed costs. When overhead costs are allocated more justly, the cost per valuations can be very revealing. The final cost evaluation is the value of ownership, and this type of evaluation begins to take into account the value of processing seen with the mainframe, perhaps not seen elsewhere. It's a more challenging type of cost and value evaluation to make, but the effort can be rewarding. The message of this chart is actually quite simple. Don't rely on perceptions of zOS costs that might have been formed in the past. The cost profile of zOS is not what it was even a few years ago. The licensing model is based on actual usage, and the presence of specialty engines, ZAP or ZAP on zip, can have a profound impact on the actual costs seen. So again, the appeal is to keep an open mind and engage a cost study to see the potential cost structure of zOS given the factors in play today. IBM has programs to help perform this analysis. Contact your IBM sales representative for more information. That's the story. WAS is WAS at the application specification layer with a strong foundation of systemz, zOS, and parallel sysplex to service the application infrastructure. Ultimately, the story of WAS zOS boils down to the value of systemz, zOS, and parallel sysplex. It's the value of those components that form the underpinning of the story of WAS zOS. WAS zOS then takes advantage of the foundation either directly, through direct exploitation of platform services such as WLM, SAF, SMF, or RRS, or indirectly, through benefits such as general reliability and serviceability. That concludes the presentation. Thank you very much.